Have you ever stopped to think that maybe underneath all the random seeming ways you can arrange things, there are these hidden patterns, these really intricate structures just waiting? What if just one simple rule, one restriction, could actually unlock a whole new area of mathematics? Welcome back to another deep dive. We're continuing our journey, our series exploring the really fascinating world of the online encyclopedia of integer sequences, the OEIS. It's just such an essential tool, I think, for anyone digging into number theory or combinatorics. Today, we're zooming in on one specific entry that caught my eye, OEIS A000266. It's often called Permutations without Transpositions. So our mission today, our deep dive, is to unpack what that actually means. Why is this sequence important in combinatorics? And how do its properties show this kind of surprising mathematical elegance? For you, especially if you're a number theory student, this should be a really concise but thorough look at permutations when you put this very specific, insightful constraint on them. Okay, so with that idea of hidden order, let's focus on A000266 itself. We should probably start with the basics, anchor ourselves there. When we talk about A000266, it's all about permutations. Now, most listeners will know a permutation is just rearranging items, but could you quickly remind us what a transposition is exactly in this context, and why its absence is the whole point here?
Certainly. Yeah, permutation at its heart is just a reordering. If you have 1, 2, 3, then 3, 1, 2 is a permutation. Simple enough. But to really get A000266, we need to think about permutations a bit differently using their cycle decomposition. This means breaking a permutation down into separate disjoint cycles. So, for example, the permutation sending 1 to 2, 2 to 3, and 3 back to 1. Well, we write that as 1, 2, 3. That's 1 cycle, 3 cycle. Now, a transposition, that's a very specific kind of cycle. It's just a 2 cycle. It swaps exactly 2 elements and leaves everything else completely untouched. So something like 1, 2, 4 means 1 and 2 swap places, but 3 stays put, 4 stays put. And the crucial thing for A000266, the defining feature, is that it counts permutations where none of the cycles in that decomposition are transpositions. No 2 cycles allowed. Every single cycle has to have a length strictly greater than 2.
Ah, okay. So no simple 2-element swaps anywhere in the breakdown. That definitely sets a clear rule for what we're counting. What about the first few numbers in the sequence? Can we get a feel for how it starts?
Yes, the sequence A00266 begins, starting with the A0, as 1, 1, 1, 3, 15, 75, 435, 3045, 24465, and it keeps going, of course. And you're right, the offset is 0, so A0 is that first term, 1.
Seeing those numbers, 1, 1, 1, then a jump to 3, then a big jump to 15, that definitely makes you wonder what's going on. Let's try and make this definition really concrete. The source material uses a great example, A3. Could you walk us through the symmetric group S3, all the permutations of 3 things, and show us exactly which 3 fit the rule and why the others don't? I think this is where people will really have that aha moment.
Absolutely. That's a perfect way to see it in action. S3 is just the set of all possible ways to arrange 3 elements. Let's call them 1, 2, 3. And as number theory students listening will know, there are 3 factorial, which is 3 times 2 times 1. So 6 permutations in total for S3. Our job is to find the ones that have no 2 cycles in their decomposition. Okay, let's list them out. First, the identity permutation, 1, 2, 3. This doesn't move anything. It's made of 1 cycle, so no 2 cycles here. So this one counts towards A3.
Right, makes sense. No swaps.
Then you have the 2, 3 cycles, 1, 2, 3, and 1, 3, 2. These move all 3 elements in one big loop. Again, no 2 cycles involved, so both of these count as well.
Okay, so that's 1 plus 2. That's 3 already, so the others must have transposition.
Exactly. Now let's look at the ones that don't count for A000266, because they do contain a transposition. There's 1, 2, 3. This swaps 1 and 2, leaves 3 alone. That 1, 2 part, that's a 2-cycle transposition, so excluded.
Got it.
Then 1, 3, swaps 1 and 3, leaves 2 alone. Again, contains the transposition 1, 3. Excluded.
Okay.
And finally, 2, 3. Swaps 2 and 3, leaves 1 alone, contains the transposition 2, 3, also excluded.
So the only ones left are the identity and the 2 big cycle.
Precisely. So when we add up the qualifying ones, the identity one and the 2, 3 cycles 2, we get 1 plus 2 equals 3, which perfectly matches the sequence term A3 equals 3. And this small example, I think, really clarifies the rule. You can see clearly we're only keeping permutations where every single cycle in the decomposition is longer than 2 elements. The aha moment, as you said, isn't just about the words in the definition, but seeing how this seemingly simple restriction, no swapping, just 2 things, dramatically changes which permutations we keep. It's like finding this elegant little structure hidden inside all the possible ways to rearrange things.
Yeah, seeing it with S3 makes it click perfectly. Okay, definition clear. So the next obvious question for any mathematician or student is, right? But how do we find these numbers for bigger sets, for S4, S5, S100?
Hmm.
That's where things like generating functions and formulas come in, right? They give us the power to calculate these. Let's start with the exponential generating function, the EGF. It's given as xp natural pi 22, 1x. What's that expression really telling us about the structure here?
The EGF. It's such a beautiful, compact way to encode a sequence like this. It's like its mathematical fingerprint. For the number theory students listening, you'll know the basic idea. The coefficient of xn in the Taylor series expansion of an EGF gives you the nth term of the sequence, an. And this specific form, xp by 22, 1x, is particularly insightful. Think about it in terms of building blocks in combinatorics. The EGF for permutations without cycles of a specific length, say length k, often involves a term like xp, xkk. So that xp by 22 term in our EGF is precisely there to remove the contribution of cycles of length 2, the transpositions.
Okay, so that's the without transpositions part encoded right there.
Yeah.
What of the 1,1x?
Right. Well, 11x is actually the EGF for all permutations with no restrictions on cycle length. You might know it also as xpx plus by 22 plus by 33 plus. So when you put them together, xp by 22, 1x, it's like you're taking the generator for all permutations and mathematically dividing out or filtering out the part that corresponds to having 2 cycles. It's a really elegant way to express that forbidden structure idea.
That's neat, like a mathematical filter. Okay, so beyond the EGF, there's also an explicit formula given for an, so ni 0.floor n2. Nice 1i, 2i. Now that looks pretty complex at first glance, but it lets you calculate any specific term directly. Can you give us a feel for what's happening inside that sum? What's the intuition?
Yeah, it does look a bit intricate, doesn't it? But it's actually a classic example of the principle of inclusion-exclusion. Very common in combinatorics. The n factor outside is kind of standard. It relates to the total number of ways to order in things initially. The real work is done by that summation, sum I 0.floor n2 manage 1i 2i. What it's doing, step by step, is starting with all permutations, implicitly by the end. Then it subtracts off permutations that have at least 1 transposition. But wait, we've subtracted too much if a permutation had 2 transpositions. So the next term adds back those with at least 2 transpositions, then subtracts for 3, and so on. The nh1i handles the alternating adding and subtracting. The I in the denominator deals with the fact that the order of these I transpositions doesn't matter. And the 2i, that relates to how you can choose the pairs of elements within those I transpositions. It's a really careful, systematic process to filter out exactly the permutations we don't want, the ones with any transpositions, leaving only the ones we do want.
It's always impressive how combinatorics finds these elegant, if sometimes complicated-looking, formulas for counting things precisely. Now, what about how these numbers behave when n gets really big? The source mentions an asymptotic approximation. An is approximately E12n. That E12 factor seems specific. Unexpected, maybe. What's the significance of that constant popping up here?
Ah, that E12 factor. That's where things get really interesting, I think. It's a profound piece of information. It tells us that as n, the number of elements gets very large, the proportion of permutations that don't have any transpositions out of all n possible permutations settles down. It converges to a specific value, and that value is exactly raised to the power of -1/2, which is roughly 0.6065. So about 60.65% of permutations for large n are free of transpositions. It's not just some random number. It's a fundamental constant appearing naturally. This E12 often shows up in probabilistic combinatorics, maybe related to Poisson distributions, or the study of cycle structures in random permutations. It hints at some kind of universal behavior governing the absence of simple structures in large random systems. It's a deep link between this specific counting problem and fundamental mathematical constants.
Wow, that's quite an insight. Connecting this discrete counting problem to E and probability like that. Okay, and for people who like computing terms iteratively, there's also a recurrence relation. It's given as an, nan, 1 plus, n1, an2, an23. This lets you find an if you know the previous 3 terms, which sounds computationally very useful. The source mentions it's a definite recurrence. What does that tell us about the sequence? Is that significant?
Yes, definite is quite significant in the world of sequences and combinatorics. It stands for differentially finite. It essentially means that the generating function for the sequence satisfies a linear differential equation that has polynomial coefficients. What that implies for the sequence an is that it's, in a mathematical sense, well-behaved. It doesn't grow erratically or unpredictably. There's a strong underlying structure. Recurrence relations like this aren't just handy for computation. They often reflect a fundamental recursive structure in the objects being counted. Many sequences that arise naturally from counting problems turn out to be definite. It's a sign of a certain kind of mathematical regularity.
Okay, that makes sense. It points to a deeper order. And here's one more connection that seems really neat, almost elegant in its simplicity. The source states that A00026616N plus AN. We know AN counts the permutations without transpositions. We know N is the total number of permutations. So what must A00027616N be counting? Is it really just the rest?
Yes, it's exactly that straightforward. It's a beautiful demonstration of complementary counting, since n is the count of all possible permutations of n elements, and an is the count of the subset of those that have no transpositions. Then A00027616n must be the count of the remaining permutations, that is, the ones that contain at least one transposition. It's a perfect split. The entire universe of permutations is partitioned into two sets, those without transpositions, counted by an, and those with at least one transposition, counted by A00027616n. It's not a complication, it's actually a simplification. It shows how understanding one property or its absence immediately tells you about its opposite. It neatly carves up the whole space.
That clarity is really satisfying. Okay, let's shift from the math itself to its history. You mentioned the OEIS is invaluable for its record keeping, and this sequence, A000266, apparently wasn't just discovered yesterday. It has roots going back quite a way.
Absolutely. It's quite fascinating, actually. This sequence isn't some modern artifact of computers. It's been recognized and studied in foundational works for decades. It even had older catalog numbers like M2991 and N1211 in earlier printed collections, which shows it was already a known quantity in the mathematical community long before the OEIS digitized everything.
Wow. So where does it show up?
We find it discussed in cornerstone texts. For instance, J. Riordan's 1958 book, An Introduction to Combinatorial Analysis, a real classic in the field, mentions it. And of course, Neil Sloan himself, the founder of the OEIS, included it in his own major compilations. It was in his first Handbook of Integer Sequences back in 1973, and then again in the much larger Encyclopedia of Integer Sequences that he co-authored with Simon Plouffe in 1995. Richard P. Stanley, another giant in combinatorics, features it in his highly influential Enumerative Combinatorics, Volume 1 from 1986.
So it's been part of the canon for a while.
Definitely. And the interest continues. There are links in the OEIS entry to extensive tables of terms computed by Alois P. Heinz, which are incredibly useful for researchers today. And there's even a relatively recent article from 2018 by Larry Carter and Stan Wagon in the American Mathematical Monthly that discusses aspects related to the sequence. The fact that the OEIS entry itself is marked as approved and, looking here, was last modified quite recently, July 2, 2025, shows it's not just a historical relic. The OEIS is a dynamic thing, constantly being updated and refined by mathematicians worldwide.
That really underscores the value of the OEIS as this living library. Okay, so let's try to wrap this up. What are the key takeaways here? We've dug into A000266, this sequence that counts permutations with a very specific rule. No transpositions allowed in their cycle breakdown. We saw how that 83 example really makes the definition clear, showing how the rule filters the possibilities. And then we looked at the powerful tools mathematicians use, generating functions revealing structure, explicit formulas for calculation, those fascinating asymptotic results linking to E, and recurrence relations.
Exactly. I think what you've seen is how imposing just one specific constraint, no two cycles within the broad world of permutations, can lead to this rich, interconnected tapestry of mathematical properties. It's not just about getting the numbers right. It's about uncovering connections to other sequences, like its complement, A00027616, and links to fundamental constants like E, and even touching on deeper probabilistic ideas about how permutations behave on average. It really highlights how seemingly simple rules can generate complex but ultimately very beautiful and structured numerical patterns.
So as you, the listener, think about A000266, maybe ponder this. How does understanding sequences defined by what they lack, like the absence of transpositions here, give us deeper insights into the overall nature of permutations? And could there be other forbidden structures, other rules about what's not allowed, that might define equally rich, equally fascinating mathematical sequences, maybe in areas we haven't even thought to look at?
That's a great question to leave with. In what other fields, maybe even outside pure math, perhaps in physics or computer science or biology, might a simple restriction, a small change in the rules, lead to unexpectedly complex and elegant patterns? The OEIS is absolutely brimming with sequences born from such questions. We really encourage you to dive in yourself, explore its depths, and maybe find your own next deep dive.